Okay, hello everybody. This is going to be lesson number 6. Please keep in mind that lessons 1 through 5 were the assignments from the summer packet. Lessons 1 through 5, which corresponded to homeworks 1 through 5. And then from this point forward, every lesson will be titled by the number and we'll have a corresponding homework assignment. So today is lesson 6. You'll do homework 6. Tomorrow will be lesson 7 and homework 7. And we'll just continue that way through the rest of the year. I think that's the easiest way to keep everything organized. So absolutely nothing in this packet is new. I was tempted to actually skip some of the parent function stuff altogether, but I figured by making you this kind of short video, it'll be good for you to kind of get used to the format, since this is the format that we're going to be using as the year progresses, and the videos will generally be a little bit longer. So this is kind of a nice way for you to ease on in. So the parent functions themselves are found in section 1.6 of your book. You probably have come across some of them throughout the first 5 sections informally, but now we're going to kind of just go through them one by one and then remind you of all the important vocabulary and the notation that you have to be using. So to start us off, there are 2 different kinds of linear functions, one of which is the constant function and the other of which is the identity function. So the constant function is f of x or y equals any constant number, in this case 2, but could be anything. The domain is, of course, all real numbers, and the graph will always look like a horizontal line. These will always have a slope of 0. The range is always a single real number, whatever the number happens to be. Again, in this case would be 2. Please take note that any of these horizontal lines would be an even function with y-axis symmetry. Y-axis symmetry, of course, means that you could fold the graph on top of itself right over the y-axis. Compare that to the function on the right, which again is the identity function. So the identity function in its parent form is f of x equals just x. That gives you the picture above. It is a diagonal line, in this case with a slope of 1 and a y-intercept of 0, 0. Of course, you can change the identity function by changing the slope, either making it steeper or less steep. You could make it negative, which would have it go the opposite direction. And you could, of course, move it up and down by changing the b, which would change the y-intercept. Notice that in this particular problem, the graph is increasing from negative infinity to infinity. This is an example of a graph that is odd with origin symmetry. In case you don't remember, even and y-axis always go together, and odd and origin always go together. Here we have the quadratic function. So the quadratic function is either y equals or f of x equals x squared. This, of course, means that no matter what you plug in, you're always going to get back something positive, which is why the graph looks the way that it does. The domain is all real numbers. And again, negative infinity to infinity, that's interval notation. So please make sure that you are always using interval notation. The range from 0 to infinity, that implies that the smallest value of the range is 0, which is included because of the bracket, and then goes all the way up to infinity. The function is even, which again means that it has y-axis symmetry. The intercept is 0, 0. It's decreasing from negative infinity to 0 and then increasing from 0 to infinity. Please remember that when you're talking about increasing and decreasing, your answer is x values. So from what x to what x is it increasing? From what x to what x is it decreasing? Or from what x to what x is it constant? Additionally, please remember that when you're doing increasing and decreasing, you always use parentheses only. You never use brackets, because if you're increasing and decreasing, well, when you get to the top or when you get to the bottom, how do you know if you're increasing or decreasing? You don't. So you always just use parentheses, and that takes the guesswork out of it. Little bit of a vocab word here, a relative minimum at 0, 0. Remember that you can either be a relative minimum or you can be an absolute minimum. In this case, 0, 0 would also be the absolute minimum, meaning that there's no way you could ever go below 0, 0. But a relative minimum means that you are the lowest point in the area. Remember that generally speaking, graphs can have multiple relative maxes and mins. Typically, that happens more for cubic functions or piecewise functions. Again, these are just the parent function form. If I was to take this quadratic and if I was to move it down, let's say that it looked like this. That's not a great picture, but you get the idea. It would still be even. The increasing and the decreasing would still be the same. The domain would be the same, but of course the range would be different. What if I was to move this graph to the left? Well, now the domain would be the same, the range would be the same, but it would no longer be even since you could no longer fold it across the y-axis. And then, of course, the decreasing and increasing would be different. So again, this information is for parent functions only, but of course that changes as the function changes. Here's your cubic function, y equals x cubed. Notice that as opposed to the quadratic function, part of the graph is positive because if you cube a positive, you get a positive. If you cube a negative, you get a negative. And of course, if you cube 0, you get 0, which makes that the x and y intercept. Domain and range, all real numbers. This is an odd function, which of course means origin symmetry, and it's increasing the whole time, which means from what x to what x? Well, that would be from negative infinity to infinity. The square root function, so it's starting to get a little bit more interesting. Notice that the domain and the range are both 0 to infinity, but brackets on both of those because you can take the square root of 0. You get back an answer of 0. So that is why you're using a bracket, which means include 0. And of course, on the graph, it would be a nice closed circle. Again, these graphs also have arrows on the end. They just don't happen to appear on these pictures. So feel free to add them in if you would like. The reason why the graph only exists in quadrant 1 is because you cannot take the square root of a negative, so you can't ever plug in anything less than 0. And if you can't plug in anything less than 0, you certainly can't get anything less than 0 out. If you were trying to plot points on this graph, certainly it would behoove you to choose the nice perfect squares like 1, 4, 9, things that you know the square root of. But don't be afraid to pick things that give you decimals. If you were to plug in 2, the square root of 2 is 1.41. The square root of 3 is 1.73. Even though they are decimals, you certainly can plot decimals almost as easily as you would whole numbers. And this graph is increasing from 0 to infinity, again, from what x to what x, and you're only going to use parentheses anytime you're talking about increasing or decreasing. Notice that it's neither odd nor even, there is no symmetry, and there is no relative max or min, since for any point that you choose, you're always going to have a point that's higher than it, and you're always going to have a point that's lower than it. Here's the reciprocal function, also called a rational function. This is where there's a bunch of different asymptotes and wholes. This gets its very own section in a couple of weeks. You probably spent a lot of time on it last year. It's one of the most important functions and certainly one that you're going to need to focus on next year in calculus. So first, let me remind you that there are, in fact, 2 asymptotes in this graph. Asymptotes are generally denoted with dotted lines. There is a vertical asymptote. Any vertical line is always x equals, which in this case is 0. Then there is a horizontal asymptote. A horizontal line is always y equals, and in this case it's 0. The reason why there's a vertical asymptote at 0 is because you cannot plug a 0 into a denominator. Therefore, the domain is every single thing except for 0, which is why the domain is written as this. Remember, the union, that u, just says there's a break between the 2 different intervals. Because you can't plug 0 in, you can't get 0 out, and that's why the range does not include 0, hence why there is a horizontal asymptote there. Again, think about slant asymptotes. Think about quadratic asymptotes. There are lots of things that's going to come up in a couple of weeks. Remember, this is just kind of a little bit of a reminder. This function is in fact odd, which means it does have origin symmetry. Again, remember what it means to be symmetric to the origin. That means if you were to take any piece of the graph from the first quadrant, reflect it over the x and then over the y, it would have to match up exactly. Another way of saying that is that quadrant 1 and 3 are always reflections of each other, and quadrants 2 and 4 are always reflections of each other. This function does not have any intercepts because of the asymptotes. And this function is always decreasing, but because of the fact that there's an asymptote, you have to go ahead and give it 2 different intervals. It's first decreasing from x equals negative infinity to x equals 0. And then because of the asymptote, you take a break and say that it's decreasing again from 0 to infinity. You always have to break for asymptotes. That's just a good rule to follow. Then finally, the absolute value function. If you were to compare this list, you'll find that it's exactly the same as the quadratic function. The graph looks very, very similar, except it's a V instead of the U. Again, domain is all real numbers. Range is only 0 to infinity. It's even with y-axis symmetry. It has a relative minimum of 0, 0, and it's decreasing from negative infinity to 0, and then increasing from 0 to infinity. Again, very unlikely that any of this was new, but it doesn't hurt to get a quick review, remind yourself of the important notation, and of course, remind yourself of the important vocab words. The truth of the matter is, tonight for homework 6, you are going to do review problems that really focus on the summer assignment. So I just pulled up a little selection here, not necessarily even to do them, but just to kind of point out a couple of things. So notice that this is question 1. So given the graph over here, which again, because it is a function in pieces, that is of course called a piecewise function. We're going to do much more with piecewise functions in the next lesson. You're being asked to find A through L for that function. So f of 4, notice that there is no equation for this graph. I do not ask you to make an equation for this graph. I might ask you at some point, but certainly not today. So when I'm asking you for f of 4, anything inside of parentheses, that is of course the x value. You will go to that x value, find the corresponding y value, and then give the answer if one exists. When I ask you function, I want to know, is it 1? Which means you will, of course, employ the vertical line test. Because there are no equations, when I'm asking you for even, odd, or neither, your best bet is to use whether or not it has any symmetry. Remember, functions that are even always have y-axis symmetry. Functions that are odd always have origin symmetry. And then if it's neither, it's neither. Y-intercept, at most there can be 1. Zeros, another word for 0 is x-intercepts or roots. They all mean the same thing, and you can have as many x-intercepts as you want. A relative maximum means that it is the highest point in the area. So if to the left of the graph, all the points are below it, and to the right of the graph, all the points are below it, that is in fact a relative max. In order to be a relative min, all the points to the left and right have to be above it. And again, you can have several of each, or of course you can have none. Tell me where the graph is increasing, decreasing, or constant. You can use I for increasing, tell me where it's happening, D for decreasing, tell me where it's happening, and C for constant. Remember that when you're telling me these answers, you're telling me in interval notation from what x to what x, and you're only going to use parentheses. Domain and range, take special attention to look at open circles and closed circles, and be sure that your answers reflect them if needed. This is now questions 5 and 6, and again, I'm only giving you a couple of hints on the ones that I anticipate you might have questions on. Notice that we're back to the even, odd, neither question, but there are no graphs in sight. One option to solve these questions would certainly be to create a graph, look at the symmetry, and then answer. Another way, of course, is to use the test for odd evenness, which means that in the function, everywhere there's an x, you put a negative x. Then you calculate, and one of 3 things will happen. So again, let's say you wanted to test A here for whether it was odd, even, or neither. You would take negative x, and it's the same test for odd, even, or neither. Everywhere there's an x, you would put a negative x, and then you would square it. Either your answer will turn out to be the exact same as the original problem, in which case you will declare it an even function, or it could potentially be the exact opposite function, in which case you will declare it an odd function, or if it's a neither, then you say that it's a neither. 6 is perhaps your first piecewise function of the year, but all they're asking you to do is evaluate it. So these are the 3 different pieces of the function, the 3 different pieces of the domain. You're only allowed to calculate each of these values in the appropriate domain. You don't do all 3, you only do the one that applies. Number 9 is a great review of domain. Again, domain is the most important or one of the most important topics that we're going to use all year long. You have no hope of accurately graphing something if you don't know the domain. So what I have for you here is a nice little matching activity. And notice that 2 is kind of the magic number. Not only do I think it's good to kind of have problems that are similar, so you can see kind of the specific differences, but I think it's also a really good review of the notation. So again, remember the 2 most important things about domain restrictions. You cannot have any value of x that gives you a 0 in a denominator. When it comes to square roots or fourth roots or sixth roots, any even root, you cannot take an even root of a negative number. So whatever's under the radical has to be greater than or equal to 0. And then, of course, as the problems get more and more complicated, as you add in denominators, as you put radicals in denominators, you, of course, have to take these 2 main rules and kind of combine them together. So I think 9 is a really nice review activity in terms of domain. So your homework tonight is homework number 6. It is a worksheet. You can find that worksheet in the class notebook. Anytime the homework is a worksheet, you will have 3 different options for how you do your work. Option number 1, print out a copy at home and then do your work right on the sheet. Option number 2, copy the page from the content library, put it into your personal notebook, and do it electronically. And then choice number 3, just do the work on a separate sheet of paper. So you don't have to tell me ahead of time how you're going to do it. You can do it a different way every time if you want, but your homework for tonight is homework number 6. And again, all of the questions on there really refer to the summer packet, but I thought it made sense to kind of do it here with this review lesson. So thanks very much, guys. This is kind of just getting used to the format. So we will see you next time.